Hello, my name is Taylor Harrells, and I'm currently a biological science student here at the University of Alabama at Huntsville. Today, I would like to enlighten you on a revolutionary new technology known as artificial photosynthesis, a system that will allow for a green and renewable production of value-added chemicals. Before we get into the nitty-gritty of this content, let me elaborate on the basic mechanistic foundation of this technology. I'm sure we have all heard of photosynthesis. It's the means of autotrophic organisms such as plants and cyanobacteria to produce usable molecules through a series of redox and anabolic reactions. This system is composed of two separate sets of reactions, the light cycle and the dark cycle. During the light cycle, the Nintendo array complex harnesses solar radiation to induce protolysis, also known as the separation of a hydrogen from a water molecule. The hydrogen from the water molecule then induces a cascade effect that travels down both cycles and provides energy to produce these value-added chemicals, such as maybe the major byproduct that a lot of people are known about is sugars, but there's also a whole menagerie of other things that could be utilized. The key concept here is the utilization of basic molecules such as carbon dioxide and water to produce more complex molecules such as sugars. The creation of artificial photosynthesis apparatus would be extremely vital for the biosynthetic production of value-added chemicals in a green and renewable way. With a system such as this, we could produce a plethora of organic compounds such as pharmaceuticals, fuel sources, maybe such as ethanol and various other things that were utilized today, flora nutrient supplements, fauna nutrient supplements, and a multitude of other biodegradable substances. Current prototypes of artificial photosynthesis arrays have been constructed and well tested in Berkeley laboratories. The current model is composed of two sets of nanowire arrays. The top set, the photoanode, is composed of titanium dioxide nanowires that act similar to that of the antenna array in natural photosynthesis. These nanowires induce protolysis of water molecules and due to their polarity carry the hydrogen-reducing agents down into the secondary layer, the photocathode. The bottom layer is composed of silicon nanowires that deliver the hydrogen-reducing agents to the bacteria that colonize them, Sporomosa ovata. These bacteria are anaerobic and utilize the hydrogen in a similar manner to natural photosynthesis to produce a molecule known as acetyl-CoA. This molecule is a precursor construction template for an immense multitude of organic compounds. This acetyl-CoA compound is then transferred to a secondary colony of genetically engineered E. coli bacteria. These bacteria have had plasmids implanted into them that allow for the biosynthetic production of multiple value-added chemicals, such as listed in the chart here, and butanol, which is an example of hydrocarbons such as ethanol that could be produced by these systems, polyhydroxybutyrate, which is actually a biodegradable plastic, and the other three, amorphidine, epiaristocylene, and catenine, are actually isoprenoid compounds that maintain pharmaceutical potential. Although currently the system has its limitations, the system can only run properly for roughly 80 hours until the sparging gas of oxygen builds up and produces an aerobic environment that is actually toxic to the bacteria Sporomosa ovata. Several methods of improvement, such as implementing facultative anaerobic bacteria, are being proposed, and the future for this technology is looking very promising. Thank you for watching this presentation and allowing me to enlighten you on this revolutionary new technology known as artificial photosynthesis. In the future, this system and systems like it will allow for the green and renewable production of much needed value-added chemicals.